Hello all and welcome back to this course on digital systems. So let's continue our discussion on a few more multi-bit circuits, right? So now we are going to look at a very common operation, again a very important operation that happens in a microprocessor, and that is basically n-bit magnitude comparison. Right? So fundamentally, we are going to assume here that the number is unsigned. Okay, comparing 2's complement magnitudes, right, is going to be slightly more complex. If it's just 1's complement, it may be okay, or if it's just the sign magnitude representation, then it may be slightly easier, right? But for now, we will just focus on unsigned comparison, right? We have two unsigned numbers, n bit, and we basically want to compare the two of them, right? So again, how would you do this in decimal, right? Suppose you have 987 and you're comparing again 964, right? What do? You basically compare the MSB, right? The MS digits, most significant digits. If they are equal, you go to the next one. Now, if one is higher than the other and they are not equal and one is higher than the other, you simply stop. It doesn't matter if there are, any more digits after this, right? You simply stop at the place where there is a mismatch and you are sure that it is higher, and this is essentially a function of the weighted sum in powers of 10 in the decimal. The same will carry over if we are trying to do the comparison in binary. Okay, so suppose I want to do 101101, right? Or I'll do 4-bit comparison with 1001, right? So of course you compare these two bits, they're the same, these two bits, they're the same. Then you come here, right? This is A and this is B, and at this point you just declare that A is greater than B, right? It does not matter. The key point is, it does not matter what this is, whether that B is, this could be 1 or 0. It absolutely does not matter, right? So this is exactly the same idea that we are going to carry forward into the comparator, right? Now, as usual, remember, you have n bits, A0 to n minus 1, an minus 1 to A0, with this being the MSB as usual. LSB, right? And then you have Bn minus 1 to B0, okay? And I'm going to look at the system which basically takes an n bit A, okay? Let's say this is 4-bit for now, okay? Or it could be n bit, okay? And then this is B, another n bit, and I'll have 3 outputs, because I could have 3 cases. Either A is greater than B, okay? A strictly greater than B, or A is less than B, or A is equal to B, okay? Now, if you want to do A less than or equal to B, then you just need to OR these two outputs, right? A greater than or equal to B, you just need to OR the first and third output. So you can, improvise on this later, okay? Comparator, right? So now, as I told you, right, in the very first lecture of this discussion with respect to the adder, of course you can do the same thing here, right? I have an output YA greater than B, okay, YA less than B, and YA equal to B, okay. So this is A and B. Now, if everything is 0, right, then of course YA equal to B will be 1, right? Both these will be 0. Now this is 0 and this is 1, or no, keep this as all zeros and B0 alone is 1. Then of course B is going to be greater than this thing, so it will be 0, 1, 0, right? And of course all of these things essentially, for each and every case here, you are going to have the same thing. B is greater than A, the same, right? So the same thing, holds, the same argument that we had for the adder indeed holds even for the comparator, because there are 2n inputs. So we have 2 power 2n combinations of inputs, right? So even if you take a 4-bit input, 4-bit A, 4-bit B, and simply do the comparison, you are basically going to get 8 inputs, which is 2 power 8. You'll have 256 combinations, and then you'll have to do the Boolean simplification for all these cases. So that's not possible and not tractable when you make it like 8-bit becomes 16-bit, 16 becomes 32, and so on. And therefore we are simply going to follow exactly this algorithm that we saw here, right? The common sense algorithm, where we are actually dealing with bit by bit comparison. Okay, so therefore let us first look at how do we build a 1-bit comparator. Okay, so I have an input A, I have B, and I am saying is YA equal to B, YA greater than B, or YA less than B. Sorry, this is all B. Okay, so we are going to say 0 0 0 1 1 0 1 1, and just like in the case of the adders, 1-bit case is always is tractable, it's easy to do, and therefore it can be implemented using truth tables. So obviously the truth table for A equal to B is 0 1 1 0, right? And now what do you have here? You have A greater than B. No, it is sorry, this is the opposite. A equal to B is 1 0 0 1. I'm sorry, right? And of course this is 0. Remember, only one of these 3 outputs, YA equal to B, YA greater than B, or YA less than B, can be 1 at a time. Okay, now YA equal to B is not true for the second case, and of course it is B that is greater than A, right? Here it is 1 0, and again this is back to 0, right? This is effectively what we have, right? Now let us go back and figure out what this, what these truth tables are, right? So let us look at YA equal to B. I am not going to draw the truth table because it's only 2 inputs. We can just write out the min terms and simplify if necessary. So this is just min term 0, A bar, B bar, or A, B, right? This is actually A XNOR B. Okay, A XNOR B, okay, which is this thing, and this is, by the way, denoted by this dot. Okay, the A XOR B whole bar essentially, right? So this can be written in the following way: A B bar plus A bar B whole bar, sorry, whole bar. Okay, this is the A equal to B term. Now what do you have here? What is A greater than B, by the way? YA greater than B is A equal to 1, okay, and B is 0. That's the only case, right? Likewise, YA less than B is A bar B. Okay, so in some sense, right, what we have out here is the A equal to B itself is actually a case of it's neither A greater than B nor B greater than A. That means A has to be equal to B. That's what this is. This is actually saying it's either A is greater than B or B is greater than A, and neither of these two. That's why that bar is on top, is basically saying the either A B bar or A bar B is true, and then when you put a bar, the either simply becomes a neither condition, right? So neither is A greater than B, nor is B greater than A. That's when A can be equal to B, right? So therefore, this implementation that we have, right, if you look at this, is actually very straightforward. You take A here and then you take B, okay? Then we have, I'm going to now generate two things. Okay, A bar. So I have an AND gate. Okay, I'm going to assume again the standard cell, right, has AND gates, 2 input, 3 input, OR gates. Okay, I'm assuming in this case there is no XOR, by the way. Okay, and then I'm going to say inverter. Okay, so I have A bar B, right, and then I have the first one is A B bar. This is A bar B, right, and then I have these two conditions which I am going to OR. Okay, this will give me the XOR condition. Okay, now you notice that this output is nothing but output Y A is less than B, because it is no, A is greater than B, because, and here this output is Y A less than B, because it is A bar into B here. Okay, and you can then right, you can then pass this through an inverter, because the XOR, doing an OR of A greater than B or A less than B, right, is still A is not equal to B. That's all we are saying. Okay, so this output is actually A not equal to B, and if you invert it, you will get Y A equal to B. Okay, so therefore, what we have first of all done is, in the process of implementing this XNOR gate, right, which basically allowed us to do the A equal to B condition, we have taken those intermediate signals and itself generated YA greater than B and YA less than B, right? And therefore, this implementation is what we are going to take forward into the next multi-bit comparison as well. Okay, so let's look at a 4-bit case, A3 to A0, A and B3 to B0, right? And we are going to basically do this generation here, and we are going to generate all the signals that we want. So first of all, let me redraw this a little bit carefully so that we get it in a nice representation, right? This is A, right? This goes into an AND gate. Okay, this is B, and So I'm going to use this structure here, okay, to generate the bits that I want, okay. So I have this going into an OR gate, coming out of an inverter, right. So I could technically I will just represent this with a NOR gate, okay. Internally I'm assuming it's an OR gate followed by an inverter, right. I'm going to just assume that, right. So I have this, and this is what I'm going to call A equal to B, okay, and this is what I'm going to call, this is A bar into B, that means this is B greater than A. Now this is A greater than B, right. So these are my, this is my 2 input 3 output. I've just redrawn it for convenience like this, okay. Now I'm going to use this, okay, I'm going to use this structure and build my 4-bit comparator, okay. So first let me make a copy of this so that okay, right. So I'm going to straight away I'm going to talk about so what is the MSB and what is the LSB is what we have to see, okay. So I'm going to assume as usual that A3 to A0, B3 to B0, this is the MSB and this is the LSB, okay. So let's start with that A3, B3, okay. I'll also put the other, so I'll keep this out. Yeah, okay. Yes, so here we are, okay. So this is A2, B2, A1, B1, A0 and B0, right. Now if my, so first of all let us look at the simplest case, okay. When can I say y A equal to B, right, equal to 1 in this 4-bit case, right. Every single bit has to be the same, right. So that means all I have to do is take all these 4 cases, right. So just to simplify my, no, I'll come back to that, right. So for now I will just say I have a NAND gate like this. So this is my AND gate and this will give me YA equal to B. Why? Because if A3 equal to B3, then this signal goes high, this signal goes high, this signal goes high and this signal goes high, right. And if all 4 of them happen to go high, obviously then A equal to B, right. So therefore, that is the first condition that is easy to implement. Now, how do we handle the case? Okay. So, what we have here is, so this one is A less than B and this one is A greater than B, right? Now, if A3 happens to be, if A3 happens to be greater than B3, right? So, it's not equal and A3 happens to be greater than B3, right? Then obviously I can conclude that my, uh, I can obviously conclude, right? Okay. So, in order to get the circuit for the A greater than B and A less than B, maybe it is useful to even write down the expression, right? So, let us call these outputs as x3, x2, x1 and x0. So, the YA equal to B, okay, is simply x0, x1, x2, x3. Now, when can YA greater than B be true, right? This is true if, first of all, the A3 case, it should be A3B3 bar, right? A3B3 bar is needed there, okay? And if that is the case, that is the MSB, A3 is 1, B3 is 0, then we are done. We just say that is A greater than B. If not, then obviously X3 should be 1. That is, it should be equal. A3 and B3 should be equal. And then you do the ANDing with A2, B2 bar. Right? Likewise, if x3 and x2 happens to be 1, then you come down and do the ANDing with A1, B1 bar. Finally, if the x3, x2, x1, then you check A0 bar, B0 bar. Right? So, this is a very straightforward thing for us to do. Likewise, when can you say Y is A less than B? You have to just do the opposite case. You have to take the other thing, right? Each bit should be lesser, that is A3 bar B3 should be true. That means A is less than B, or X3 and A2 bar B2, or X3, X2, both bits are same, A1 bar B1, or X3, X2, X1, the previous one is A0, B0 bar. Here it is A0 bar, B0. Okay. So, effectively what I need to do now is to implement exactly this particular case on the left hand side here, right. So, let us start with this expression. I have, this is the lower one is going to be A greater than B. Okay. So, I will just run that line here. Okay. I am going to give this input to a huge OR gate. Okay. And then what I need to do is, I need to, if x3 is 1 and A2 B2 bar, right. So, here what I have to do is, I got to take this guy right. This is what is the AND gate. Okay. Then I need to do x3 and x2. Okay. So, for that I have another AND gate here, which is, I am sorry, oh, this is this correct? Yes, this is x3 and x2, right. So, I can have another AND gate here, right, which is x3 and x2. right? And I'm going to say and this is going to come as one of the inputs to this OR gate, right? And finally, I have x3, x2 and x1. So that will be a 4 input AND gate like this, okay, which is basically x3, x2, x1, and then I have A naught, uh, I have A naught and B naught bar, right? So that is my fourth thing, and this comes here and I get this output. So this is YA greater than B, okay? So this is the, the A greater than B part. Similarly, you can go ahead and construct the exact counterpart that you want for the other, for the top signals, that is the A less than B part, that is A3 bar. You can take these signals here and do exactly the same, right? If you'll have another 4 input OR gate, 2 input, 3 input, 4 input AND gates, and then you OR them out and you'll get a corresponding, so I'll just draw the OR gate here, right? YA less than B, right? And of course, one of the inputs will directly come from, this thing, right? So if you look at this, maybe this I'll use a different color. Okay, one of the inputs, I leave it as an exercise to the viewer to actually figure out how to go ahead and implement the remaining 3 inputs to this 4 input OR gate. This is the 4 input, 1, 2, 3, 4, okay. So there you will get Y of A less than B, YA less than B. So with this, what we have been able to do is again simplify a multi-bit implementation by simply looking at a bit by bit Boolean expression and implementation that we wanted, right?